our V in versus our V out and stuff. What actually happens then is our VC is going to start out high. Wrong. So now when we're looking at it, we said that our voltage of our capacitor and the voltage of our inductor, those both went up to approximately our 2.059 volts AC. Our source voltage is going to be, our source voltage is really actually way down here. This is where we're going to be at 100 millivolts AC. That's where here's where our source voltage is. Here's our actual voltage of our capacitor and inductor. Let's see, I should change that up here. Because of that. Change that up that side. Not entirely true here. Let's see, how do I want to draw that up? You know, my inductor is going to start out. Inductor is going to start out. Inductor is going to start out, go up. And then once I get past my resonating frequency, that inductor is actually going to start to drop back down. It will actually end up going, depending on if I keep on increasing my frequency, my voltage of my inductor is actually going to go way up. It's going to go up to the 2.059, and then it'll go eventually get down to my 100 millivolts again. And then my voltage of my capacitor is going to look just kind of very opposite. It's going to go up. It's going to peak out. And that one's going to eventually kind of stabilize out. I'm going to have to do it on my spreadsheet here. I think that's going to be the easiest way here. That way I don't have to try drawing it up nice and clean. This would be a, so I'm going to zoom in on this.
Capacitor goes halfway up and then drops down.
So what we got is a little easier to see. This isn't with the correct values, but it's but we can throw that correct values in there after we kind of talk about it. So my blue one is going to be my voltage of my resistor. The green one is my voltage of my can't see that here. Yeah, so this is going to be my total voltage of my inductance. So it's the combination between both VC and VL. So that's my green one. Then I have my VL, which is my orange. And then my DC, which is my yellow. So when we're starting out at a very low frequency, and this is what I'm trying to draw up, but I couldn't quite get it. So if I'm taking a look at my yellow is my voltage of my capacitors. It's going to start out at approximately my source voltage. It's going to go up, and then when I start getting close to my resonating frequency, then it's going to shoot way up. It's going to induce a larger voltage at this point. And then as I keep on increasing my frequency, then my voltage of my inductor, or my voltage of my capacitor, ends up going down to 0. My voltage of my inductor, which is orange, starts out very low, starts to go up, and then when I hit my resonating frequency, you can see all of a sudden this thing just all of a sudden starts to react. It shoots up to that 2.059 volts AC, and then as I keep on increasing my frequency, then it's going to drop down and then drop the source voltage. So right at this point, right where this thing gets to be a really high peak there, and the voltage gets to be really high, if I'm looking at my blue one, or my green one here, this is the sum of my two voltages. The voltage of my capacitor and the voltage of my inductor. And right when those two peak out, and I add those, algebraically add them up, you can see that that green line is going to spike down to 0 volts. And that's right at this point here. That's right where I hit my angle of 0 degrees. And so those two voltages ended up canceling out across each of the inductor and the capacitor. And then the only thing that it leaves then is the voltage across the resistor. And so then you can see that all of a sudden the voltage of the resistor, which is my blue line, all of a sudden spikes up to my source voltage. Then I get past my resonating frequency, and then it stabilizes back out and goes back down to 0 volts. So the only time I get any voltage across my resistor is just during this little short during period when my VC and my VL cancel each other out. But voltage across my voltage of my inductor and the voltage of my capacitor is going to be at its maximum voltage at that point, so right in my resonating frequency. And so you can kind of see nothing really happens at my lower frequency, and then all of a sudden I get to my resonating frequency, and then all of a sudden the whole thing starts to react, and then I get past my resonating frequency, and then it kind of just stabilizes back out. But it gets very active at this point, right at my resonating frequency. One thing about my resonating frequency is depending on what you have for your inductor and your capacitor, right when I get to this point here, a lot of times you'll be, if you're listening to, if you got some kind of a device or something like that, all of a sudden you'll hear a high-pitched whistle, depending on what the resonating frequency is. At that resonating frequency, that's where those inductors and stuff, the capacitors, are starting to work with each other, and they'll start to resonate. They'll actually start to vibrate and make whistling noises. I know if you get something around like a 33 millihenry and like a 0.1 farad capacitor and stuff, I know that a lot of those circuits will start to actually whistle. You'll start tuning it in, all of a sudden you'll hear nothing, then all of a sudden get your resonating frequency, and then those things will start to vibrate and start whistling, give you a high-pitched whistling. As long as it's within the, less than 20 kilohertz, so it's in your audible hearing range.
Is that what, when tuning the station on ham radio sometimes, or shortwave, is that what that?
Sometimes it can be with that, that you might be hearing that, yep. You're tuning it in, yep. Yeah, that's a little bit different, but it's kind of the same concept. Yeah, so the complexity of the circuit, right when that happens, things really change at that point. We'll come back to this circuit here. So, yeah, you're kind of lucky. We used to make this in class. Before we got to the lab book, we would go ahead and we had to go ahead and make our own RLC spreadsheet so that we can, because when you get into dance class, then this will all come back to haunt you again, because you'll be working with these circuits again in dance class. So I would make the students make their own little spreadsheet and stuff and come up so they can graph it all out and stuff and make it so it's changeable. But we'll take a look at that coming back here. Alright. So that's what's happening when we get to when we get to our resonating frequency. Those things are gonna start to spike up. I'm gonna draw nothing saying. Let me draw this one more time here. So BC down. A little easier after I see it now. The DL starts off very low. That stays very high. So we'll say red is VL and my green is VC. And then we'll make purple ER. There you go. All right, so now what we want to do is there's a couple things that we want to take a look. First of all, we want to find out what the quality of our circuit is. And when I'm talking about the quality of the circuit, that has to do with the relationship between our reactance and our resistance. And that quality of that circuit is going to affect how sharp of a point that is. If I have something that has a large amount of resistance in it, this thing gets wider. It gets wider. My bandwidth gets wider and stuff like that. If I have a very good Q, then I get a very, like on the one that I was just showing you with my spreadsheet there, how it's very straight up, very pointed. That's going to have a good high quality circuit. And that quality depends on what our bandwidth is. And our bandwidth is going to be what's our allowable frequencies that we allow coming out of our output. And remember, our output has to be something greater than 70.7% of our voltage source. And then we want to find out where at the bandwidth, where is my lower frequency cutoff and where's my upper frequency cutoff. So to calculate out your quality then, so the quality of your circuit is based on the resistance, so Q is equal to R over, X of L over R. Sure I have that right. Yeah, X of L over R. So we know that in my resonating frequency, X of L equals X of C, so it really doesn't matter if you use X of L or X of C, because that's our inductive reactance on either one of those components. So X of L, we use X of L because that already has a quality of its own, because it has its own resistance and stuff. So we just kind of use X of L over R to come up with our number. It's just a ratio, it's just a number, there's no units for it or anything like that. So we're just going to take X of L, which is going to be our 4,613 kiloohms, and divide it by our total resistance of 224 ohms. So this should be really RT. Get that in there. So what do you get for your quality of circuit there using those numbers?
20.59.
So you get 20.59, and that's all it is. It's just a number. There's no units. It's kind of funny watching people on the final. It just drives them nuts not to have a unit on there, and so they'll try coming up and making up units and everything for just put a unit on there. But it is. It's just a number. That's all it is. It's just a ratio. All right. So once we find out what the quality of our circuit is, then we can go ahead and we can figure out what our bandwidth is. So our bandwidth then is just going to be our bandwidth is just going to be our frequency, our resonating frequency divided by our Q. And that'll give us, and that's going to be in, and that's going to give us it to us in hertz. Thank you. 35.65 kilohertz. 65 kilohertz. Okay? So if I take my resonating frequency of 734.1 kilohertz divided by the quality of my circuit, that's going to be the bandwidth that I'm going to have. So right here, this is at this point right here, this is going to be my resonating frequency. My bandwidth is going to be half on this side and half on this side. So I'm going to have a total bandwidth, and that's going to end up being somewhere, one thing bad about these circuits, it's hard to, so I'm going to, this isn't really the proper way of doing it, so I'm going to just do it so we can see it. So our bandwidth, this is going to be our lower frequency cutoff. Other half of our bandwidth is going to be on our upper frequency cutoff. So we're going to have our FL, our frequency, our lower cutoff, and our upper frequency cutoff. And that bandwidth is right here. That's what our bandwidth is equal to. It's between those two numbers there. That's where our bandwidth is coming in. That's going to be our allowable frequencies that are going to pass in out of our output of our circuit here. That's going to be any of those frequency within that bandwidth, half of it below our resonating frequency and half of it above our frequency is going to allow it to go into our output. And that's going to allow those frequencies to go into our next stage. So to calculate out your frequency, your lower frequency cutoff then, is all I have to do is I just take my bandwidth, divide by 2, and then just add it to my resonating frequency, and then do the same thing except, and that'll give me my lower frequency cutoff. Now if I just take my resonating frequency and subtract half my bandwidth, divide by 2, will equal my, I got those backwards. This will be my upper frequency cutoff, and then my lower frequency cutoff. So we're just taking our bandwidth, we're just dividing it by 2, adding it to our resonating frequency, that'll give us our upper cutoff, subtract half of our bandwidth below it, and that'll give us our lower frequency cutoff. So what do we get for our lower frequency cutoff?
Lower. Is that right?
That's
Lower or the upper?
Either one, do whichever one you calculate out.
Yeah, the lower at 716.2 or 3.
716.3
Yeah.
Oh, that's
kilohertz?
right, I got the kilohertz.
Go back to that. 716.3 kilohertz. And then the upper one is going to be, so that looks about right. So half about that, that'd be right. And then what do you get for the upper one? 751.9 kilohertz. Yeah. Yeah. All right. So that's our bandwidth. That's going to be, so that's going to be right here. So I'm going to have, on my lower frequency cutoff, I'm going to be down to 716.3 kilohertz. My upper frequency bandwidth is going to be at 751.9 kilohertz. My total bandwidth is going to be 35.65 kilohertz. So if I had a radio station that I'm going to listen to, my resonating frequency, the radio station I'd be tuning into would be approximately, let's just say 734.1 kilohertz. But I could go ahead and my radio would actually tune into anything that was between 716.3 kilohertz and 751.9 kilohertz. We have to have some kind of a bandwidth in there so that I don't have to exactly tune my radio and right at that precise frequency. Otherwise, that thing is going to drift all the time. You would never be able to maintain your radio station. So we have to have some kind of a bandwidth. We have to have allowable bandwidth. And we kind of come up with a quality of our circuit. Depends on what our bandwidth is. And so for this particular circuit, the only thing that we're going to go into our next stage then would be anything that's greater than 716.3 kilohertz, but less than 750.9 kilohertz. Everything else is going to be rejected. Even though all these other frequencies are coming in, bombarding our circuit, that's the only frequencies that it's going to allow to pass on to our next stage. And then we go into an amplifier stage and start amplifying that out. And so this is our bandwidth. This is going to be where we're going to be this is going to be our frequency cutoffs. So my frequency cutoffs is also something else that happens right at this point. This is where my axis C or my BC right at this point is going to equal to 70.7% of my voltage source. That's going to be my lower frequency cutoff. On my lower frequency cutoff, I'm going to have a certain angle. What do you think that angle is going to be? If I'm at my lower frequency cutoff, what do you think my angle is going to be? So let's see, how would I want to, so here I'm, let's see, what would be a good one here? This is where X of C is going to be greater than, so am I going to be more, at my lower frequency cutoff, am I more capacitive or more inductive at that point? So here's, so you remember here's VC, my red is VL. So I'm more capacitive, right? Because I start out very high, right? I'm very high, but my inductor is very low at that point. So even though they start to both climb at this point, I'm still going to be a little bit more capacitive at that point. And so if I'm more capacitive, and I'm at my lower frequency cutoff, what do you think my angle would be at? Just throw a good round number on there, something that you might have asked from the last previous labs.
45 degrees.
45 degrees. Positive or negative?
Negative.
Negative 45, yes, because we're going to be
More capacitive.
We're going to be right down here. We're going to be more capacitive. We're more down this way, so I'm going to be at negative 45 degrees at this point here. Then as I keep on increasing my frequency and I get past my resonating frequency, then now my VL stays high, right? As I keep on increasing my frequency. So right at this point here, I'm going to become more what? Capacitive or inductive?
Inductive.
More inductive, and I'm going to have an angle of what?
Positive 45.
Positive 45 degrees. Those are my frequency cutoffs. This is going to happen where, and all these voltages are going to happen, so any of this voltage at this point then is going to be approximately 7.7% of my voltage source. Now, like I said, this isn't to scale so you can see the bandwidth and stuff like that, because my voltage source, remember, is way down here. So really my bandwidth is realistically right across there, right across my resistor, but so we can see it and spread it out. But we know that my lower frequency cutoff is going to be at 70.7% of my voltage source. I'm going to be at a negative 3 dB of gain. Okay, we're talking about gain. We can either have a voltage gain, my V out over Vn, or I can have a power gain of my power out versus my power in. So we can look at it two different ways. But at that point, I'm going to be at a negative 3 dB at my frequency cutoffs. Then at my resonating frequency, then I'm going to be equal to my source voltage. Because these two components are going to cancel each other, and then I become purely resistive, and I'm going to be at 100% of my voltage source, ideally. Other than for the voltage drop across the resistance of the windings of the inductor. But that's our bandwidth. These points happen at negative 45, plus 45, so that's going to be my bandwidth. That's what the angles are going to be. They're going to be at 70.7% of my voltage source. It's going to be a 3 dB cut. And that's going to be my upper and lower frequency cutoff, so it's my resonating frequency. So then when you get into Dan's class then, so what he's going to do is he's going to have you actually put these into practical circuits. You're going to be building a radio receiver, shortwave radio, and you have to go and analyze that circuit and find out exactly what's being filtered out through those different stages on using the filters. So we kind of give you the old basic how to do it. Here's how they work. Remember, we've got bandwidths, we have quality of our circuits. Certain things to remember, that resonating frequency, my angle is going to be at 0 degrees. X of L is going to equal X of C. VR, or BL is going to be equal to BC. ZT is going to be equal to my total resistance. Those are all things that happen at my resonating frequency. Let's see here. Just take a look and see if there's one other thing I need to do. Yeah, I think that's... Oh, so by the way, that one formula that I told you wasn't on your sheet that I handed out, that one with all the formulas on there. The one that's missing is that calculating out your resonating frequency. So make sure you write that on there before your final. That's the one that's missing, and I love watching that person that didn't write it down there, and he gets the sheet, and all of a sudden he'll go like this, he'll start banging his head, and he'll try thinking about what that. That's the one that we started out with. That was the first compilation. So if you don't have that one, doing the rest of what's that? Yep, square root of LC. Yep, make sure you have that. Let's see here. Yeah, I don't know. I can't think of. But if you want to see kind of change up the way we do lectures and stuff, especially when we get into solid state. So I think what I'm going to do is that Mondays I'm going to have you be required to come in, do the lectures on Mondays, get your iClicker in, do the first lecture, and then if you want to see more, if you want to go through another worksheet and stuff. Some of you guys are going to catch on to this right away. You don't need to be here this on Tuesday. I'll just open up the lab day. But I'll go and I'll do an optional lecture day for anyone else that wants to go over this information one more time. That way we're still doing lectures for 2 days, but not everyone needs to be here on Tuesday. If you got a pretty good grasp on it, you don't need to any more extra help on it. That's fine. I'll open up the lab. I won't be able to do checkoffs while I'm doing lectures, but I'll do your checkoffs on Wednesday, or when I get done with lectures on Tuesday, I'll try getting in there and doing the checkoffs and stuff. But Mondays, I always want you to be here so we can kind of go over some of the key points. And then on Tuesdays, we'll just go ahead and we'll do another worksheet or whatever and go through some more of the advanced materials. We can go over the parallel circuits and the filters and stuff like that. So tomorrow I'll open it up. If you want to be here, great. If not, you can get the rest of it from your reading, which you should be able to now. You should be able to get it from your reading. Go ahead and do that. You can go right into the lab. But for anyone that wants to see a little bit more or want to do a parallel circuit or talk about the filters and stuff like that, we'll take it to the next level tomorrow. But one thing about the parallel circuits, again, once we understand how a series circuit works, we can do the same thing with a parallel circuit. So remember, on a series circuit, we said that current remains constant in series circuit, right? So at 0 degrees, you know, IR, IC, and IT were all at 0 degrees, right? So when we were doing it for a parallel circuit, your vectors is basically the same thing, except this time it's going to be your voltage source, your voltage of your capacitor, voltage of your inductor, and the voltage of your resistor are all going to be at 0 degrees. And then what's going to change is that you'll have IC up here. Remember, these get kind of flipped around. So IC is going to be up here, IL is going to be down here, and then you're basically, instead of calculating out what your total reactance is, you're going to calculate out what your total conductance is. So remember that you're going to have to calculate out, you know, R is G. You're going to have BC up here for your conductance, and BL for your conductance for your inductor. Those are all going to be there. So it's still the same way of handling it. It's just that we got to remember what remains constant in a parallel circuit, our voltage. So that's all going to be at 0 degrees. Series circuits, it's our current. And then we just got to flip these around. If we're doing a parallel or a series circuit, you just flip those things around. Parallel, we're looking at the current for our vectors. Series, we're looking at our voltage. So otherwise, they get calculated out basically the same way. But there are some a little bit more advanced filters and stuff like that, and we can kind of take a look at those tomorrow. All right, any questions on that? Does everyone have a pretty good grasp on that? All right. I don't think I have anything more, but if you want to see some, if you need extra help here today, you know, we got till 10 o'clock. Or if you want to do another one of these tomorrow, you know, just be back here at 7:30 and we'll go through this in class again for anyone who wants to see another one or look at a parallel circuit. One or the other. All right, so I'll open up lab tomorrow. We got 2 days left of this week, Tuesday and Wednesday, and then we're off for 4-day weekend for Thanksgiving.